So currently we are studying our fourth unit, that is image segmentation, and today we are going to study thresholding based image segmentation, and under that we are going to study global and local thresholding. And actually we have studied thresholding operation in our second unit under the topic point processing. So you are actually familiar with the thresholding operation, but how to use that for the segmentation task, that we are going to study today. Okay, so we know that after applying thresholding operation we get a binary image because its transformation function is like this. We are familiar with this notation S of T of R. This T is our transformation function, R is our intensity level in the input image, S is the intensity level in the output image. So on the x-axis we have the intensity levels of the input image represented by R, and on the y-axis we have S, the intensity levels at the output image. And the transformation function of the thresholding operation is like this. Okay, so if we have the pixel value lesser than k, we are assigning 0 to that pixel. Okay, so if the intensity level of that is greater than 127, we are assigning 1, otherwise 0. Okay, so at the end of thresholding operation we get two level binary images. Okay, so this is the working of thresholding operation, and for some simpler images like this we get a better segmentation results as compared to more complex operations like region growing or canny edge detector. For the simpler image, thresholding will work fine. Okay, let me show you the second example also. Okay, so here we have a lighter object embedded on the darker background. Okay, so for such simpler images this thresholding operation will give us a better result. And why we are interested in thresholding operation? Because it has, so let me write it down. So we are interested in the thresholding operation because of two reasons. First one is the simplicity of implementation, and second reason is the computational speed. Okay, so why? Because now here we are working on the individual intensity level. Okay, we are not considering a neighborhood around the pixel, right? Okay, so that's why it is having a better speed, computational speed, and it is very simple for the implementation. That's why we are interested in thresholding operation. And how to decide whether to apply thresholding or not? So for that we can simply plot the histogram of the given image, and if you have such hills, so if you get such hills in the histogram image, then easily we can set the threshold as this value. Okay, middle of this valley. Okay, so these hills are known as modes. So remember this terminology, these hills are known as modes. Okay, and this is actually a valley region. Okay, and we set the threshold to the midpoint of this valley. Okay, so if we have such histogram for the input image, we can apply the thresholding operation and perform the segmentation task. Okay, so this is our T, threshold is represented by T. So f of xy, if the intensity value of the current pixel, okay, pixel at xy coordinate, if it is greater than T, you assign 1. Okay, and if it otherwise 0. Okay, so here what we are assuming that the range of intensity levels covered by the objects of interest is different from the background. So this is our assumption. Okay, so we are assuming that our object and background are having different intensity levels. Okay, if they are having a similar intensity levels, then the thresholding is not going to work. So if we have such case, we will get different modes for the objects and background, and then we will set a threshold and we can segment the object from the background. Now what if we have multiple objects in our image? Okay, if that image also satisfying our assumption, then we will get different modes for different objects and separate mode for the background, and then we will set multiple thresholds, okay, and we will segment the different objects from the background. Now this type of segmentation thresholding is known as multiple thresholding. Okay, so this is known as multiple thresholding, and when we have a single threshold, okay, which is constant for entire image, that is known as a global thresholding. Okay, so just like our global variable and local variable, so global variable is like visible to all the functions, right? So similar to that, this global threshold will be applicable to all the pixels. And if we have multiple thresholds in an image, if we set multiple thresholds, that is known as multiple thresholding, and this will be the equation for multiple thresholding. Okay, so if the value of the current pixel is greater than the T2, we are assigning a value, okay, and if it is between these two thresholds, okay, we are assigning b value, and we are assigning c value to our background. Okay, generally we represent thresholding using this equation. Now t is a function on our spatial coordinate xy. This pxy is actually representing neighborhood, so it is a local property of this point. So neighborhood around that xy, average gray, it can be average gray level of neighborhood, and f of xy is actually the intensity level of that particular pixel. Okay, and so if thresholding problem requires multiple threshold, are best solved using region growing methods. Okay, so if we have multiple objects in an image, then better to go for the region growing methods as compared to thresholding. Okay, why? Because if you have multiple objects, then their modes will start overlapping. Okay, and then it is very hard to find the threshold for individual objects. Okay, so it is better to go for the region growing method if we have multiple thresholds. Let us discuss different types of thresholding. So we have discussed global thresholding and multiple thresholding. So if the threshold value, if it is constant for entire image, that thresholding is known as a global thresholding. If that t is changing over an image, that is known as variable thresholding. Okay, so if we have different t for different regions in an image, then that is known as variable thresholding, and under that we have two categories, that is local thresholding and adaptive thresholding. So what happens in local thresholding? So if t depends on both f of xy and p of xy, so if you decide the value of t based on the intensity value and the neighborhood, that is known as local thresholding. So because you are considering the local properties of the region also. And second one, if t depends on only the spatial coordinates. Okay, so if the t, you are determining the t based on the coordinates only, that is known as adaptive thresholding. Now if there are more than one threshold, that process is known as multiple thresholding. So now the success of thresholding depends on these 5 parameters. So we know the basic one, that is the modes of these objects should be separable, right? So then only you can decide the threshold value, and then you can perform the thresholding. That is obvious. So separation between the peaks, okay, that decides the success of thresholding. The further apart the peaks are, the better the chances of separating the modes. Second one is the noise contained in the image, the noise content of the image. Okay, so what happens when you have a noise in an image? So let me show you the previous example. Yes, so now if we have zero noise in this given image, then for the object you will have one spike, okay, in the histogram, okay, and for the background you will have one spike. Okay, but what if we introduce noise in this image? Then it will start broadening your modes, and ultimately if the noise is too much, then this mode will start overlapping. Okay, then you cannot determine the value of threshold accurately. Okay, so that is how the noise will affect the thresholding. The next one is relative sizes of the objects and background. Okay, so if your object is very small, then the number of pixels will be very less, right? Then its mode will get overlapped by the background. Okay, consider there are very less pixels representing the object. Okay, the pixels, the background pixel may cover that peak, that mode. Okay, then there also you will find it difficult to decide the value of threshold. The next one, uniformity of illumination and reflectance. So we know that the value of f is made up of two components, the illumination and reflectance. So this we have studied in our unit number 2. Okay, so if we have uniform illumination of the source, then it will affect the thresholding. This I will explain through one example. Okay, so here we have same example. So it is a role of noise. Okay, so this is the image with zero noise. Okay, as you can see, we are getting good spikes for the object and for the background, and this is our valley, and we can set the threshold. Okay, and easily segment this image. Now here we have introduced a Gaussian noise. Okay, with the zero mean and standard deviation of 10 intensity levels. As you can see the effect of this noise on the modes. It is broadening the mode. Okay, and if the noise is too much, so here we are having a noise with zero mean and standard deviation of 50 intensity levels. Now see the histogram. Now the histogram of both the modes is overlapping. Now it is very difficult to find the threshold. The basic algorithm of thresholding cannot decide the value of threshold here now. So this is how noise can affect the thresholding operation. Now this is the effect of illumination and reflectance. See here, this is our this image is used for this example. So it is the image with Gaussian noise with zero mean and 10 standard deviation. Now here, as you can see, we have ununiform illumination. So illumination is decreasing from right to left. Okay, and this is the intensity values of illumination. Now as you can see, the part of this object is brighter here and darker in this region because of this ununiform illumination. And if we plot a histogram of this image, okay, we are not having two separate modes. We are not having two separate modes for background and objects. So this is how the illumination and reflectance will also affect the output of thresholding. Now under thresholding, for the segmentation, we are going to discuss these 4 techniques. Okay, starting with the global thresholding. So 2 techniques are based on global thresholding. So both the technique will have a single threshold. Okay, then we are going to study variable thresholding. Under that we are going to see adaptive thresholding and local thresholding. Okay, so first we are going to study this iterative algorithm for global thresholding. So we know that global thresholding uses a single threshold. Okay, and this algorithm is capable of estimating the threshold value automatically. So we don't have to set the value of threshold. This algorithm will itself calculate the value. Okay, so see the algorithm. So initially select an initial estimate for the global threshold t. Okay, you set the value of t randomly. So actually in reality we set this t equals to mean intensity level. We find the mean intensity level and that value is set to t. Then second one, segment the image using t. Okay, this will produce 2 groups of pixels, G1 and G2. Okay, now we'll calculate the mean value for G1 and G2. Okay, some pixels will fall in G1 group and some pixels will fall in G2 group. So we'll calculate the mean of those pixels, and then we'll update the value of t using this expression. Okay, we will find the average of these two means. Okay, and this is the iterative process. So then we will repeat this number 2 and 4, okay, steps from 2 to 4 until the difference between the values of t in successive iteration is smaller than predefined value delta t. So we have to decide this value. Okay, so if it is not if it is smaller than this delta t, then we will stop. Okay, so let me explain this through one example. Okay, so now consider initially we have set value of t as this one and number of iteration or delta t as, let's say, 10. Okay, so now this is our t, initial value of t. So now pixels in this region will fall in G1 and remaining pixels will fall in G2. Okay, then we will find the mean of this. Okay, so it will be around this value and mean of this will be here. Okay, then we are going to update the value of t using this equation. Okay, then it is average of these two value, then t will be updated to, I think, somewhat here. Okay, then in next iteration it may come here and then here, and ultimately the change will be smaller than 10. Okay, then ultimately we'll reach to that optimal t value. Okay, and then we'll stop. Okay, so this is the working of iterative basic global thresholding algorithm. Very simple. So these are the two examples of that. Okay, now let us see second method of global thresholding, that is known as Otsu method. Okay, so I am expecting a question based on Otsu method. Okay, so it performs better as compared to the iterative method, but the derivation is little bit complicated. So Otsu method is aimed to find the optimal value of global thresholding. Okay, so now this Otsu method is capable of finding the threshold value when we have overlapping modes. Okay, so it will find a better threshold value as compared to our iterative method for such cases. So it is based on interclass variance maximization. Okay, so it tries to maximize variance between two modes. Okay, so we will find the variance of this region and this region. Okay, and it will try such groups with highest variance, interclass variance. Okay, so we know that for calculating variance we have to find mean, right? So we will find the mean. Okay, so this is the derivation of Otsu method. Okay, so consider we have m by n image. Okay, and we have L intensity levels. So this multiplication m into n is equals to n0 plus n1 plus so up to nl minus 1. Okay, so this n0 is representing number of pixels with intensity 0. It is a number of pixels with intensity 1, and last it is a number of pixels with intensity level L minus 1. Okay, so this summation will be equals to m by n, right? Then we are calculating a normalized histogram. So this we have studied when we learned histogram matching, right? So this is the equation. So this is the number of pixel having the ith intensity level divided by total number of pixels, right? So this is the probability of the pixel having ith intensity level. Okay, so we know this equation, and if we find the summation of this I pixels, okay, varying from 0 to L minus 1, obviously we will get 1, right? Okay, because this ni, summation of ni will be m into n divided by m into n, that is 1. Okay, now suppose that we select a threshold k. Okay, now we will be calculating this equation for different values of k, and we will decide that k with the highest interclass variance. Okay, So now suppose that we select the threshold as k. Okay, k will be between 0 and l minus 1, used to threshold the input image into two class. Okay, so now we have obtained two classes, c1 and c2. Now let us calculate the probability p1k that the pixel is assigned to class c1. Now what is the probability of the pixel assigned to c1 class? So it will be a summation of probabilities from 0 to k. Okay, so what is happening? So this is our 0, this is our l minus 1. Okay, we have set k as the threshold. Now what will be the probability of these pixels? So it is a summation of these pi's, right? And this pi will be smaller than this k. Okay, so this is the probability of pixel assigned to class c1. Similarly, probability of class c2 will be simply 1 minus this value, right? Or you can calculate in this way also, from I varying from k plus 1 to l minus 1 pi, or it will be 1 minus this, right? Then so we are calculating the mean intensity value of class c1 represented by m1k. Okay, so now see here, I varying from 0 to k, I into probability of, this is the conditional probability, right? Probability of I given class c1. Okay, and this we have expanded using a Bayesian equation. So if you remember the Bayesian equation, so it is probability of A given B equals to probability of B given A into probability of A divided by probability of B. Okay, so we have expanded this. Okay, now here what will be the value of this probability of C1 given I? So is this I, so C1 is what? It is a collection of pixel lying between this range, right? So now I value is between 0 to k, right? So this value is actually 1, because this all the pixels are lying in C1 only, right? So this part is 1. This p of I is represented by this small case notation, and this probability of class C1, this we have calculated here. Okay, so this is represented by p1k, so that is taken outside. Okay, so this is how you can calculate the mean intensity of class C1. Okay, so I repeat, so for expanding this equation we have used Naive Bayes equation. Okay, and this probability is actually 1. Okay, this pi is represented by this smaller notation, and pc1, so this is nothing but this probability, and which is written outside. Okay, so this is mean intensity of C1 class, and this is the mean intensity of C2 class. Okay, then we will calculate the variance. Okay, before that we have to calculate the cumulative mean of entire image. Okay, sorry, first up to level k. Okay, so it is calculated using this equation. Okay, from 0 to k, I into pi, and average intensity of entire image. Okay, so it will be varying from 0 to l minus 1, I into pi. So this is represented by mg. Okay, and now this is using this equation we are calculating the global variance. Okay, so we know that how to calculate variance. So we subtract the current value from the mean, right, and the square of that. Okay, so this is how global variance is calculated for the entire image. Global variance, it will be for entire image. So intensity value minus the global mean, square of that into its probability. So this is our global variance, and between class variance. Okay, so now we have two classes separated by threshold k. Okay, so we'll calculate the variance of this and this, so which is represented by m1 and m2. Okay, this p1 is the probability of class 1, probability of class 2, and using this equation we are calculating between class variance. Okay, now we are using this one variable. Okay, we want its value to be high. Okay, because the between class variance should be high, right? As you can see here in this equation, if this subtraction, this m1 minus m2, if it is higher, then between class variance will be higher, right? And what is this m1 and m2? It is mean intensity level. Sorry, let me show you. Yes, so mean intensity level of C1 and mean intensity level of C2. Okay, so if you have two modes, okay, so this will be m1 and this will be m2. So if their subtraction is higher, that means m1 and m2 are apart, right? Okay, so if the difference is higher, okay, so they are more away from each other, right? So that means this sigma, the variance between the class, will be higher. Okay, so which is calculated with this variable. Okay, okay, so this is the measure that we have introduced. If so, we will select that k value with the highest n value. Okay, it will have higher between in between class variance. Okay, and then we'll decide that k value. Okay, so let me summarize the Otsu algorithm. So first we will calculate the normalized histogram. Okay, so how we will normalize the histogram? So that is n by m into n. Okay, then compute the cumulative sums. Okay, using equation number cumulative sums. So this is the probability of that class. Okay, so this is calculated. Okay, p of 1k. Then compute the cumulative means. Okay, for both the classes m1 and m2. Then compute the global mean. Okay, so we have seen the equation global mean. Okay, then compute the between class variance. Okay, which is represented by this one, and then obtain the Otsu threshold k star. Okay, this k is actually varying from 0 to L minus 1. Okay, we are assuming k to be every value, every possible value. Okay, obtain the Otsu threshold represented by optimal value. Okay, k star as the value of k for which this in between class variance is maximum. If the maximum is not unique, obtain k star by averaging the value of k corresponding to various maxima detected. If there are multiple k's having the same value, you take the average of that. Compute the global variance using equation that we have just mentioned, this one, and obtain the separability measure n star by evaluating equation this with this value. Okay, so this is how Otsu method works. So here we find the in between class variance and we select that threshold value having the highest in between class variance. Okay, and this is the result. Okay, this is input image, this is the histogram. Okay, now as you can see, these are the objects, so we are interested in these objects. Okay, now so we have very less number of pixels for the objects. Okay, so they are overlapped here. Okay, and this is the result using iterative algorithm, and this is the result using Otsu method. So this image C is segmentation result using the basic global algorithm, and this image D is the result using Otsu method. As you can see, we are getting the better result for the Otsu method. Now let us talk about third type of thresholding, that is adaptive thresholding. Now in adaptive thresholding, so if you remember, adaptive uses only spatial coordinates. Okay, so now we are talking about adaptive thresholding. So here we will be just considering the spatial coordinates of the image and not the neighborhood. Okay, so now this is our input image. and this is its threshold, and it is having a noise, so a noisy shaded image, and it is corresponding histogram. This is the result of iterative global thresholding algorithm, and this is the result of Otsu. As you can see here, some error is there for the Otsu method and for the iterative algorithm also. Now, how to get a better result using adaptive thresholding? So now here we have divided that image into 6 sub regions, okay, and if you find out the histogram of those 6 sub regions, you will get these histograms. Now as you can see, all the modes are very separate here in these sub regions, okay. So now based on these spatial coordinates, we can apply separate Otsu method on these sub regions, okay. So we will apply Otsu method on this sub region, okay. Then as you can see, Otsu will perform very better on these sub regions because modes are very separate, right? They are distinguishable, right? So if we divide that image into sub regions and if you apply Otsu on individual region, then as you can see, we are getting a better result, okay. So this is the example of adaptive thresholding. Now second category under variable thresholding is local thresholding, okay. So now in local thresholding, we use this P of xy. This P of xy is actually a neighborhood property of that pixel, okay. So now consider this example. So this is our input image, and this image is actually the image of multiple thresholding, result of multiple thresholding. As you can see, for this we have set intensity value as 255. For this we have set the value as 127, and for this we have set the value as 0, okay. So this is the result of dual thresholding, multiple thresholding, and this is image of local standard deviation, okay. So now for the local thresholding, so which criteria we have used here? So along with f of xy, we have used this criteria. So this is actually a p of our p function, predicate function. So if the current pixel is greater than this, sigma is actually a standard deviation of the neighborhood around xy, okay. If it is greater than this, and this m is actually mean around mean of neighborhood around xy, if it is satisfying both the condition, then we are deciding, we are selecting, and along with this we will compare the intensity value also, okay. So we will consider both p of xy and f of xy, okay. So this is how we can apply local thresholding, okay. So this is another example, okay, but here we have used moving average, okay. Thresholding, local thresholding based on moving average, okay. So what is the procedure here? So here this is our handwritten text image, okay, and here we are having a spotlight effect. As you can see, we are having the brighter region in the center and darker in the corners, okay. So this is with a spot shading, this image is with spot shading, and this is the result obtained using Otsu method, okay. As you can see, the information in this part is lost, okay, and this is the result obtained using local thresholding using moving average. So now what is the working of this moving average? So here we scan the input image, okay, row by row, but in the zigzag manner, okay. So in this way we'll scan the image, okay, and we'll keep finding the running average, okay. And why we are moving in zigzag manner? Because if we are, okay, now this pixel and these pixels are neighbor, okay, and if you calculate moving average in this regular manner, okay, then this pixel and this pixel is not neighbor, right? So this moving average will not work if you go like this, okay. So that's why we go in zigzag manner, okay, and we'll keep calculating the moving average, and this moving average value will be used for the thresholding. Okay, so and this is how we can overcome that problem. This is another example of moving average. Okay, as you can see here, we are having a sinusoidal shading effect. Okay, so we are getting the peaks and valleys of the shades. Okay, and this is the result of Otsu method, and this is the method of moving average. Okay, so in this way we have completed our fourth unit.